Hello everyone, I'm Parikshit Saraswat from Naughty Dog, and today we're going to be looking at some of the low-level optimizations that we did in our new game, The Last of Us Part 2. This is one of the levels where most of the traces and most of the figures in this presentation come from, except for Water Run. And what we're going to be looking at is case studies of some of our expensive passes like subsurface scattering, application of probe lighting, getting GBUFFER water. There are tell like what the scenario was, what the problem was, how we fixed it, and why that worked. The total optimization that we got from this was a saving of 2.1 ms, which considering that the frame budget is 33 ms, and these are all low-level tweaks that don't incur any artifacts or any impact on visual fidelity, it's pretty significant. And all the figures in the slides come from Razer GPU traces base PS4. Looking at subsurface first, it had a decent L2 hit ratio, but it was a memory bound pass. So the basic optimization to make the performance better would be to minimize the VGPR pressure by spilling VGPRs to LDS, decreasing their lifetime, and increasing the occupancy, thereby fitting more wavefronts on the register bar. This hit quite a bit of memory read latency, and we got more instructions every cycle. And you can see that just by increasing the occupancy of one, our performance increased by 31%. So this is a pretty low-level tweak that you can do in case you're not thrashing the L2 cache. But even with reduced GPR pressure, it's still a low occupancy shader, and the problem with low occupancy shaders is that they don't really get scheduled very well with other async processes. So since this is a memory intensive shader, we were trying to run it with another shader which had a lot of ALU, so we could hide the memory stalls even further, but this wasn't getting scheduled with it at all. So the way we went about that is by switching to pixel shader. It gives us a lot better wavefront distribution, and it decreases the memory stalls because all the writes in a pixel shader go through the color cache instead of L2. So we will have more L2 available for reads in a pixel shader compared to a compute shader. The thing is, if you try it out on a shader that is memory intensive and it needs more L2, but it's just running by itself, it will end up being slower, most likely if it's a branchy shader because of ordered export stalls. Basically, all your exports in a pixel shader have to be ordered. So a pixel shader that doesn't really write anything, it's not a skin pixel, it just wants to export 0. It still needs to wait for all the pixel shaders that have been dispatched before it on the CU in order to make its own export. So you end up with a lot of stalls, and by itself, the shader might end up being slower. So in case you're running any shader that is just running by itself, you don't need to run it with any async work to hide the memory latency even further. Prefer a compute shader if you have a lot of branching in any early layouts. You can see in our case, the instructions per cycle was almost half, performance was almost half also. Memory read stalls went lower, but export stalls were through the roof. But since the pixel shader has much better wavefront distribution, it can actually get dispatched with the async work. We were able to hide those export stalls and not worry about them at all, because during those export stalls, we could do the ALU and memos of the async shader. So they would be more or less gone, and we can hide some of the memory latency also by the ALU from the async bus and end up with an overall improved instruction issue rate. Further add hardware stencil testing to it, because now we didn't have a stencil bit for skin, but we divide our geometry into foreground and background, and most of the cases only foreground have skin pixels. So we remove all the waves that are for background geometry. That way we can decrease the number of wavefronts that are dispatched while getting better memory reads, while getting better wavefront distribution. So we were able to end up with a shader that was almost 5 times faster than the original. And in most of the cases, it was also almost free. It became that fast. So this ended up a pretty good optimization for us. The only tricky thing with this is that the pattern of pixels in a pixel shader wavefront is not a perfect tile like that in a compute shader. And in our shader, we kind of depend on this because each tile has a light list, which can be different. So if you're spanning multiple tiles, you might end up having different light lists, which can cause subtle artifacts. So what we do is that we look at our light frustums of all the local lights, and we look at the bounding volumes, compute if there's any intersection in the two. If there's no intersection, meaning the skin characters are either completely outside or completely inside of the local lights, then we don't need to worry about different light lists per tile at the first place. So then we kick in this optimization, and it is kicked in most of the game. The next pass we're looking at is the probe lighting one. So we've already computed our probe lighting, and now we just need to apply it. But since the probes can be accessed randomly all over the place, we end up with a pass which is pretty memory intensive, and it ends up thrashing the caches quite a bit. So we can't increase the occupancy in this case, because if we do, we will end up with even more simultaneous memory reads and even worsening the L2 cache thrashing. So the first thing that I did was shift to a pixel shader, made more L2 cache available. The L2 cache ratio went a little bit higher, not that much higher, but still the cache thrashing decreased a little bit. And all our writes were going through color cache. But due to branching, obviously, and pixel shaders already export stalls, shader by itself was slower, but since this was a pixel shader and it had a much better wavefront distribution now, we could hide those export stalls, and some of the memory, well, it was still thrashing L2, so the memory stalls were quite huge, but we could still hide some of it by the ALU and memoffs from the async code and end up with a slightly faster shader overall. It was just 5% increase, but it was still slightly faster just by shifting it to a pixel shader from compute shader. Now you can see here the export stall has obviously increased from 0 to 0.89, the number of difference waiting every wave cycle for export, but the overall shader is faster. So now we can increase the performance even more since we have a shader that's running well with others, but still trashing the L2 cache. We should consider decreasing its occupancy by increasing the lifetime of the VGPRs. So the way we do that is by clustering all our memory reads together as early as possible. So the more memory reads you cluster, the more VGPRs it uses, because it will increase their memory lifetime and they will end up living way more than they're actually needed. Plus, you can use the ALU in the shader themselves to hide some of the memory latency instead of hiding the latency by doing more simultaneous memory reads and adding to the cache thrashing. So this way, we can increase the VGPR lifetime, decrease occupancy, and hide some of the latency using ALU. The same for SSR ray matching shader, because during the ray matching, we were sampling the depth buffer all over the place and thrashing L2. So decreasing occupancy for that helps a lot as well. And here you can see that the number of wavefronts waiting every wave cycle for memory reads has almost gone down to half. Instructions per cycle has increased, and we got a 13% improvement over our earlier pixel shader version. Now we come to skinning. So we perform most of our skinning transformations on GPU, and what we were doing initially is that since each thread can read the same bone again and again, we were trying to read all the bones to LDS first, and then have all the threads sync, do a group sync, and then read from that LDS in order to kind of save memory reads. But it's not always good. In our case, we had different kind of shaders, so each shader has different microcode. So each time a new shader gets dispatched on the CU, the first wavefront will suffer a lot of instruction cache misses. So you will see like 7-8 instructions depending on instruction size, and then a gap of like 300 cycles. 7-8 instructions and 300 cycles, which wasn't very ideal. And if you have a lot of different shaders, so different shader microcode, and if you don't have that much work per individual type of shader, then all your like 14, 15 waves will end up getting distributed across the two shader engines. and you will end up with each wavefront being the first wavefront on that CU, and end up with a ton of instruction cache misses or synchronization bits. So for us, it was better to repeat all these expensive memory reads than use LDS and thread groups at all. So even if even if the next thread reads the same bond as the one before that, we ended up with better instruction cache hits by doing this. And our instruction cache hits went up by around 22%, and our performance went up by 24%, as you can see here. So depending on the scenario you have, if you have the same shader that you're doing and you're doing dynamic branching, then in your case, maybe it might be worthwhile using a large thread group size and using LDS to store the bone data in an intermediate buffer. But in our case, since we had a lot of different shader microcodes and not that much work per individual microcode, we ended up with duplicating our memory reads. And also, after skinning has already been done, we do recomputation of our mesh normals. But since we are sampling our data loading from the buffers all over the place, we thrash L2 quite a bit. I think the L2 cache hit ratio was around 5%. So with the obvious optimization to go would be the one similar to the probe lighting one, where we decrease our occupancy and cluster our memory reads together and try to use the ALU in the shader itself to hide the memory read latency. But this shader didn't have that much ALU. So we had to decrease the occupancy a lot. And you can't just increase the VGPR lifetime and decrease the occupancy from like 10 to 3, unless you're using a lot of VGPR somehow. So we needed to reduce its occupancy while leaving as much of the register file empty as possible for the async work running with it, because it's not a shader that was running just by itself. Now we could limit the number of waves that the scheduler dispatches on each shader engine, but this would also limit the number of waves of the async work, and we didn't really want to affect that. Throttling can create some gaps if you throttle it too much, plus it's tricky to get a specific desired occupancy. Like we saw from our tests empirically that an occupancy of 3 was giving us the best L2 cache hits ratio and the best instruction per cycle rate and the best performance. So we wanted an exact occupancy of 3. So the best way we thought was to increase the resource utilization of the shader. Now we need to keep the register pressure as low as possible. So we decreased our VGPR and SGPR lifetime as much as possible, so decrease the GPR pressure. But we added some dummy LDS usage, like we weren't doing anything with that LDS. We were just reserving it in order to tell the scheduler that, hey, please don't dispatch more than 3 waves of the specific shader. So this works pretty well. It worked great for us, but if you have async work that needs to use a lot of LDS, it probably isn't the optimization for you. So here you can see that we went first with clustering our reads and using the tiny amount of ALU that we had, but the performance didn't move that much. Like we got a 6% benefit, which wasn't ideal. But when we went with reserving LDS and decreasing our occupancy to 3, we got almost 10 times better L2 hit ratio, and we got over 3 times better performance from the original one. So those were the scanning and subsurface and volumetric probe lighting. Now we come to GBUFFER. GBUFFER is pretty huge. So we do have a lot of async work that goes with the GBUFFER, but since it's so big and since a lot of async work kind of depend on the results of the GBUFFER, we can't really fill up the entire like 10 ms of GBUFFER with async work. So almost half of it is empty and running by itself. So we could never hit our full GPR allocation. Because our GBUFFER class has a lot of interpolants. So now 2 things can happen with a lot of interpolants. Either you have a lot of small geo and you are vertex bound, and you basically end up with a large amount of vertices with which result in a very small amount of pixels on screen. So in this case, you would have a lot of vertex shaders that want to export and you will become parameter cache bound. Or you could have the second case where you have a very small amount of vertices, which can happen if you're standing right in front of like a big wall, but it's resulting in a lot of pixel shaders. So this, you might think that we could achieve full GPR allocation in this case, but even in here, we were ending up being LTS bound, and we could have supported an occupancy of 8 based on a register file, but we would only have like 5 waves on the SIMD at a time. So mostly, since we have a lot of small objects, we were parameter cache bound, but in some cases we were also LDS bound, depending on the size of the geometry. But the bottom line is we had a lot of interpolants. We could never fill up our level register file and not enough async work to fill the entire GBUFFER. So we thought we might as well spawn extra vertex shaders, even though they won't be able to export, they won't be able to do anything, just sit there, but they will still be able to do the tiny amount of ALU and mem ops they have for free. Because our GPRs are just sitting there, the pixel shaders had ordered export stalls, and we had a lot of register file empty. So we could kind of do those extra ALU and memos of the shader for free. And now, one more thing that helps is that since the goal is to fill up the register file as much as possible, what you'd ideally want to do is maximize the occupancy of your vertex shaders. Now, this might come with either spilling to LDS or spilling or just decreasing the lifetime of VGPRs, depending on how many big objects you have, depending on how much LDS bound you are. You might need to approach maximizing the occupancy based on your scenario. In our case, we were mostly bound by the parameter cache because we have a lot of vertices in our scenes. We ended up spilling VGPRs to LDS mostly. And one more thing that we didn't do, but you could do, is if you can suffer the accuracy, you can transfer some of your per pixel shading work per vertex shading, make your vertex shaders even more expensive, and end up with more of these free ALU and more of these free mem ops. We didn't try that out though, but still we ended up having more active VGPRs, and obviously the number of wavefronts waiting for export went through the roof when we did that, but the overall execution speed was around 2% faster. Now, if your vertex shaders are more expensive, ours weren't that expensive, but if yours are, you would get even better saving from this. And the next pass was water rendering. Our forward water rendering was using both early Z and late Z. But the thing is that we were expecting to see like around 4 waves per SIMD, but we would only end up with like 2 or 3 waves per SIMD. And most of this decreased pixel wave throughput was because of the depth testing speed in the early Z. So because of that, we could never hit full occupancy. And in these cases, since our water shaders weren't that expensive, we benefited by switching from both early Z and late Z to just late Z. This increased our pixel wave throughput. So this would depend on your scenario, how expensive your shaders are. If they're cheap, then you probably will have more savings from increasing your pixel wave throughput than from doing more of the pixel shading work that would have failed in early Z. But in some cases, your shader might be too expensive. So you kind of need to remove them in early Z, which was the case for us for our snow rendering. So in that case, you should use both early Z and late Z, but for us, for water and also for alpha rendered geo, we ended up using only late Z with increased pixel wave throughput, with increased number of VGPRs used. And this helped increase the performance by 15% for our forward rendered water. Conclusion is that for a 33 frame MS frame budget, if you can get over 2 MS of savings just by utilizing the hardware better, with some small level tweaks that don't cause any artifacts, don't cause any visual impact, and it's pretty considerable, and you should try to identify similar scenarios in your games and maybe use similar optimizations. And they might help out a lot, considering these are global code optimizations, not just for scene specific. And then these were some of the optimizations that helped us to maximize fidelity while running at a target frame rate of 30 FPS. These are the individual savings we got from each class. You can see skinning has the most savings by increasing our L to cache hit ratio. GBUFFER not that much because our body shaders weren't that expensive, but it's still a tiny bit, still better than nothing. So you should still try incorporating that in case your body shaders are significant. And hopefully you can identify similar scenarios, and these optimizations would help you, them being general enough. I'd finally like to acknowledge Vincent, Huber, and Autumn for teaching me so much over the year. They'll be sponsoring hundreds of questions, and the entire Naughty Dog studio for creating the awesome franchise. Thanks a lot, and hope you all have a safe day.